Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture 2A, part 3, and we're going to call this video 4D. And this is the limiting distributions of using moment generating functions. So far, we've talked about how to approximate the binomial distribution using the Poisson distribution and the sample size and value of p that are acceptable as criteria for a good approximation. We covered the definition of convergence, which is applicable to our central limit theorem, and then we convergence and distribution, that should say, and then we talked about Scheffe's theorem, which makes dealing with convergence and distribution easier. Some examples. Hopefully you've reviewed the Taylor series video, but in any case, for this video and forward, you're going to need to understand Taylor series, and you'll have some problems that require you to use Taylor series and the remainder. All right, so let's go ahead and get started. Okay, I hope you had a chance to review the Taylor series expansion and remainder theorems in the supplementary video for this course. Even if you don't want to review the whole video, which is about 40 minutes long, but it gives you a real good review of the Taylor series and expansion and remainder theorems all at once. If you don't want to do the whole thing, at least look at examples 1 and 2. You might be tempted to look at example 4 as well. So, like I said, it's very important that you know that, because you're going to have to use them in homework problems and probably on the test. So we're now going to look at the limiting distribution of x bar. This we've seen before, but we're going to look at it. We've seen the moment generating function of x bar before. We proved this in an earlier section, but I wanted to restate this theorem. So let x1, x2, and x up to xn be a random sample from some distribution with mean mu. By the way, this means that, remember that d dt of m of t at t equals 0 is equal to e of x, which in this case we're saying the mean is mu. So this is m prime of 0 is another way of writing that. All right. So we have a random sample from a distribution with mean mu. This distribution, if the distribution has a mgf, let's say m of t, where it exists for t around 0, in some neighborhood around 0. This is an open interval from negative epsilon to positive epsilon, and epsilon is some positive number. Then the mgf of x bar, and remember x bar can be written this way, is given by this formula. And again, we went over this before. So it's m of t over n raised to the nth power. So now we're going to do a Taylor series expansion of m of t over n around 0. Now this is like our x value, okay, for f of x, right? And around 0 means that a is equal to 0. And now it says there exists a number t1. This is going to be our c, because we're going to have, here's a, here's c, and here's x. So t1 is going to act as our c for a remainder. And this is a 0 here. Okay. So we can write this in the Taylor series expansion. Remember that f of x is equal to f of a plus f prime of a times x minus a plus f prime prime of a x minus a squared over 2 factorial plus dot dot dot. Okay. Well, we're just going to use the first term here, and then this will be r of, so this is where n is equal to 0, so this is going to be r0 of x, okay? And remember that r n of x is equal to f to the n plus 1 derivative at c, not at a, over n plus 1 factorial times x minus a to the n plus 1. All right. So if we look at this in this case, remember that we're doing it for m sub t. So we have, here we have so if r of 0 is going to be the first derivative, because 0 plus 1 is 1. So this is going to be m prime of c over 1 factorial, which is 1, times t over n, that's our x, minus 0 to the 1. So this is going to be m prime, and c here is t1. So m prime of t1 times t over n. And that's what we have right here. Okay, so let's continue. Clean this up so it doesn't get confusing when we do the proof here. Okay, so now you know that this, how we get this expression. The book doesn't really tell you, except it just says something about the Taylor series, and it gives you the T1, and that's it. So it doesn't tell you the rest, and I think it's important that you put this together. Okay, so remember that m of 0 equals e of e to the tx at t equals 0 is equal to e of e to the 0, which is 1, which is e of 1, which is 1. Expected value of a constant is a constant. So that's how we get m0. M of 0 is always equal to 1, and we've said that, but that's something that you need to know. For any function, it's 1. So that becomes a 1. All right, so that's how we get that. And then we're going to prove how we get the rest of this. Okay? So what we're going to do is we say we have m t over n is equal to, now we have m of 0 plus, now we're going to add and subtract m prime of 0 inside this bracket. Okay, so we've got m prime of t1 minus, or we can say, do we want the plus or minus? We want to pull out the plus, so we'll say minus m prime of 0 plus m prime of 0. So we've added 1. And now we're going to pull out this term here. And so this is equal to m of 0 plus m prime of 0. Don't forget that you have to multiply it by this, t over n, plus m prime t1 minus m prime of 0 times t over n. Now, we've already said that m0 is equal to 1, and then m prime of 0, we noted that that's going to be mu, because that's how we get e of x to the r is equal to d dt r dr of m of t at t equals 0. That's our definition for how we find the moments. That's why this is a moment generating function. So m prime is going to be mu times t over n plus, now we have this m prime of t, so we're going to write this as m prime t1 minus m prime of 0. We can put the t on top and n on the bottom. And so now we have proven this. All right, so there's that. All right. Now, we want to note that m prime of t is equal to d dt, not d dx, but d dt of e to the tx. And this is continuous at 0 in this case, because it's defined there around in the neighborhood around 0, and m prime of 0. Oh yeah, we said that. So it exists. So since t1 is between 0 and t over n, notice that as n approaches infinity, then this term is going to approach 0. This is going to go to 0, and so we're going to have 0 t1 between 0 and, by the squeeze theorem, that's what we call this, then t1 approaches 0. Okay? This means that the limit as n approaches infinity of m prime of t1 minus m prime of 0, this means that this is going to m prime of 0, right? Because So m prime of 0, because t1 is approaching 0 as n approaches infinity. And so this term is going to approach, so this, the limit of this is equal to this, which is equal to this. So in other words, m prime of 0, or m prime of t1 minus m prime of 0 is going to approach 0, that difference. Okay? And this means that if we take the limit, remember in this section we're taking the limit of the MGF, so we're taking the limit of the MGF of x bar, which is given here, and we're rewriting it as we've shown above here. That means that we can rewrite this as e to the b. So limit as n approaches infinity, and I'm going to have 1 plus, and I'll have mu t plus, and then I'll have the stuff in brackets, all divided by n raised to the nth power. Okay. So we have all of this raised to the nth power, and so this term here is the exponent. This is going to be e to the exponent of this. So that's what we have here. We have e to the mu t, that's the first term, plus, and then we need to write this as the limit as n approaches infinity, and this goes to 0, we just said. So this limit is equal to, so just this portion, that limit is equal to 0, so we end up with e to the mu t, and don't forget that t is between negative infinity and positive infinity, so it exists for all things. So the moment generating function of m sub x bar of t is equal to e to the mu t for t in all real numbers. And this is the MGF of what we call a degenerate distribution with all of its probability or mass at mu. Okay. In fact, if you look at this, this looks similar to a normal distribution. Okay. So the MGF of a normal distribution, it looks similar to that. Okay. So the distribution of x bar approaches mu as n approaches infinity. In other words, we could also write, so since we say x bar approaches mu as n approaches infinity, we can subtract mu from both sides and end up with x bar minus mu approaches 0 as n approaches infinity. Now, to keep this from converging to 0, we need to multiply it by some function of n. Okay? And so we have here x minus mu, so we've multiplied this by square root of n over sigma, as you can see here. Okay? And then we can rewrite this by multiplying by 1, which will give us square root of n, that's n x bar minus n mu, okay, over sigma times the square root of n. And remember that x bar is equal to the sum of xi over n. So if we multiply that by n, these cancel out and leave us with the sum of xi minus mu over sigma square root of n. So that's another way to write w here, okay, in this case. So recall that a standardized random variable with e, so recall that w is a standardized random variable, and a standardized random variable has a mean of 0 and a variance of 1. So for each positive integer, and so this is true for each positive integer n. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.